took me a couple minutes to set up because I wanted to make sure I was still capturing everything and I'm capturing the right screen, and I believe that I am. Okay, so now we're going to talk about gluconeogenesis, which, good news for you guys, it's really just kind of the opposite of glycolysis. So there really isn't too much more to learn except just a few additional reactions. So let's just talk about the word gluconeogenesis. So we have gluco, right, glucose, neo, new, and then genesis, which is to make. So it's basically making glucose from new. So first, let's just talk about sources of glucose. When you eat a high carbohydrate meal, right, your blood glucose levels are high, and your body, basically all tissues of your body is going to undergo glycolysis to get ATP out of it. So during fasting, that source of glucose is going to be coming from other sources. So during the fed state, you have high levels of glucose, and so that exogenous levels of glucose is going to be used in glycolysis. And then as the glucose levels are depleted in the blood, then that the blood glucose still needs to be maintained. And so after a period of time, glycogen begins to break down, so that way it can provide glucose to your blood, and your body begins to undergo gluconeogenesis. Okay, so in the fasting state, glycogen and gluconeogenesis is going to be important for supplying glucose to the blood. Okay, so as I've mentioned previously, the brain really depends on glucose. Glucose is going to be the primary fuel for the brain. And so we have been biologically programmed such that our blood glucose levels never gets too low. Because if our blood glucose levels gets too low, which is called hypoglycemia, this can lead to a coma. We can die from having too low of blood glucose. So our body has ways of sort of shifting or transitioning our bodies to become more gluconeogenic rather than being glycolytic. So when the blood glucose is low, it's going to increase glucose production, and it's also going to slow down glycolysis, right? We don't want to continue doing glycolysis throughout the rest of our body, right? Because that's going to eat up all of our glucose. So when we have low blood glucose levels, we undergo glyconeogenesis, and glycogen breakdown increases. The other thing that happens is that our body actually starts to use alternative fuel sources. So things like fatty acids and ketone bodies begin to become metabolized by our body. So our hearts, our muscles, they start to use these types of fuel sources during the fasted state. So this is really what happens for the rest of the body, but not the brain. The brain is it's really greedy, and it's going to take the glucose. It's going to utilize the glucose. So glucose is always spared for the brain. Okay, so gluconeogenesis. Here is kind of a diagram that shows the pathways of glycolysis and gluconeogenesis. So we know that in glycolysis, glucose, through a series of 10 enzymatic steps, is converted to 2 pyruvate molecules. In gluconeogenesis, the opposite happens. So pyruvate is converted to glucose. So we basically have, instead of a catabolic pathway, we have an anabolic pathway where something small, pyruvate, is being made into something large, glucose. Gluconeogenesis is something that occurs mainly in the liver cytoplasm. So not all of your organs do it, just your liver, the cytoplasm of your liver. Your kidney does a little bit of gluconeogenesis, but not very much of it. So your liver it's actually doing a lot of work to supply glucose to the brain. So I actually think of the liver as being probably one of the most important organs in coordinating metabolism. In gluconeogenesis, pyruvate and other 3 or 4 carbon sources are converted to glucose. And like I said, it's kind of the reversal of glycolysis in that it uses most of the same enzymes, and it's just that the reactions are occurring in the reverse direction. But it's not the exact reversal. Now, pyruvate, we know at this point that it's a product of glycolysis, but this can arise from other sources as a starting point of glucose production. And we're going to see that where other sources of pyruvate is coming from at the end of the lecture. So, like I said, gluconeogenesis is not the exact reversal of glycolysis because some of the reactions are irreversible. And so these reactions have to be bypassed in gluconeogenesis. Okay, so remember that in glycolysis, there's 10 reactions. These are the 10 reactions. And there's 3 reactions that are irreversible. So their delta Gs for those reactions in glycolysis are really large and negative. So this is going to be reactions 1, 3, and 10. And so we can't reverse those reactions in gluconeogenesis because they're irreversible. And so these reactions have to be bypassed in gluconeogenesis with different reactions and different enzymes in order to make glucose. Okay, so we're going to go over the first bypass reaction, which is the reaction in which pyruvate is converted to phosphoenolpyruvate in gluconeogenesis. So this would be sort of the first steps of gluconeogenesis. And so this would be bypassing step 10 in glycolysis. So the conversion of pyruvate to PEP actually requires 2 separate reactions that uses 2 separate enzymes. And so in the first reaction, pyruvate is going to be converted to oxaloacetate. So this is an intermediate that you haven't seen before, a molecule that you haven't seen before. And then the oxaloacetate in a second reaction is converted to phosphoenolpyruvate. So we're going to go over these 2 reactions separately. And these are energy requiring reactions, so they consume ATP. So the first reaction is the conversion of pyruvate to oxaloacetate. The enzyme that catalyzes this reaction is called pyruvate carboxylase. Okay, so called because it's going to take pyruvate and carboxylate the substrate. So it's going to add a CO2 group to make oxaloacetate. And it's going to use this cofactor called biotin to assist with the transfer of that carboxyl group. So biotin is going to have a very important role in the coenzyme. Okay, so we're going to go over a little bit of chemistry of pyruvate carboxylase because it's pretty cool. So pyruvate carboxylase, it actually has 2 sites of chemistry, and both of those sites are going to involve biotin. So here is the active site of the enzyme, and here's site 1, so that there's some chemistry that's going to happen there, and site 2, so here's another area of chemistry. And there's this lysine residue that's situated in between site 1 and site 2. Okay, this lysine is actually covalently bonded to biotin. So here's biotin here. It's covalently bonded to that lysine. So we call this the biotin arm because it's going to swing back and forth from site 1 to site 2. So the first thing that happens is bicarbonate comes into site 1, it becomes phosphorylated, okay? And so that's going to activate the carboxyl group of bicarbonate, and then the carboxyl group is transferred to the biotin in site 1. So biotin is going to act as a CO2 carrier. So now we have this carboxyl biotin enzyme intermediate. This whole thing is going to be swung over to site 2 to do the rest of the reaction. So here we have this carboxyl biotin arm in site 2. Pyruvate comes and binds into the active site in site 2, and then the CO2 is transferred to pyruvate to then form oxaloacetate. Okay, so biotin, right? It's going to be very important for carboxylation reactions. It's going to transfer carboxyl groups to different molecules. So if you have a deficiency in biotin, you can actually have quite a few different symptoms. You can get alopecia, which is baldness, dermatitis, anemia, ataxia, which is, did I say that right? Ataxia, which is a lack of coordination, and seizures. So this is just an example of some scientists that took a lab mouse and they were able to make it biotin deficient. So you can see that that mouse, it doesn't have any hair, it's bald, right? It has alopecia. And so after biotin supplementation, it's able to regrow that hair back. And so eggs are rich in biotin. In case you ever wondering why is biotin important, or why is there biotin in my vitamins? Okay, so we're just going to finish up with the second reaction of that step 10 glycolysis bypass reaction, which is conversion of conversion of oxaloacetate to phosphoenolpyruvate. So this is catalyzed by an enzyme called phosphoenolpyruvate carboxykinase. We just call it PepCK for short because it's such a long name. And in the chemistry, what happens first is oxaloacetate is decarboxylated, resulting in an electron shift, and then it's phosphorylated to make phosphoenolpyruvate. Okay, and so GTP is going to be the source of the phosphoryl group. So this is really an equivalent to ATP. And so that's how we went from pyruvate to PEP in 2 enzymatic steps. All right, so I'm just going to end it there because we are now at the end of class, and we'll finish up gluconeogenesis on Wednesday.